you everyone for joining us in this very first talk, a public talk at the new office of the Infosys Science Foundation. We're doing this talk in collaboration with the National Center for Scientific Research, NCBS, and the Bangalore International Center, a series on climate, energy, and renewables that we are just beginning on, making a very hopeful beginning with talks. Hopefully the next talk will be at BIC, but this is the first and the inaugural talk. And with us here to begin it is the chief scientist, Dirk Smit from Shell, and Professor Vijay Raghavan, former professor emeritus, Professor Vijay Raghavan, who was also the former chief principal scientific advisor to the Prime Minister. We're very pleased to welcome both of them here today to begin our series on climate. Thank you.
Yes. Good evening, everybody. It's wonderful to be here. I was at this venue a few weeks earlier. When was that, Bhavna? Last month, when the building was inaugurated. And it's such a welcoming and warm place. At that inauguration ceremony, Chris Gopalakrishnan, the current head of the Infosys Science Foundation, one of the founders of Infosys, and Ravi, who's the head of the Bangalore International Center, and I had a discussion. And at that panel discussion, which followed that inauguration, and also when Chris spoke, he pointed out the need for us in Bangalore, all our institutions, to come together and not just talk down and communicate as people often want to do, but actually interact with our society, thought leaders, decision makers, people at large at different walks of life, and so on. And we felt at that time that a really good venue to do that would be the Bangalore International Center and the Infosys Science Foundation, because traditionally when we talk about science and people and science and society, the talks tend to be in scientific institutions, and in some ways you're talking to an audience which has already heard the essence of the talks, and therefore you're not reaching out to interact. Now, this talk today by Dirk Smit, the chief scientist of Shell, and I'll introduce him shortly, is what we hope to be the first of a series of talks on climate change, sustainable development, and energy. And that aspect of these other issues which are very, very pressing today. And one of the major challenges we face in dealing with such complex issues is that while they are very pressing on a planetary scale or a regional scale or a national scale, if we go outside our buildings and talk to people on the street, as it were, in their top 10 problems which they list, climate change will not be at the top. They are worried about their jobs, health, food sources, employment, career paths, and so on and so forth. Of course, the consequences of climate change, extreme weather, and so on affect them. But directly about what we need to do is not really something which concerns people at large on a day-to-day basis, even though that is increasingly happening in many parts of the world. It's happening in many parts of the world, in areas, in countries where there is substantial development, and therefore people have the opportunity to consider these issues in a manner which don't necessarily affect their lives. For the rest of the world, the challenge is how does one combine sustainable development with the kinds of practices which are needed to mitigate the consequences of climate change and adapt to them, and so on and so forth. So that's a big challenge. Another major challenge which we face today is the challenge of our public spaces. When we elect our officials at the city, at the state, or the national level, we elect them with expectations that they will solve our immediate problems, and they will also work to address these immediate problems. And often solving these problems requires immediate solutions which are distinct from those which require addressing the long-term solutions which need to be taken for climate change and extreme weather and so on and so forth. So how does one balance that? We also have a situation where when we look at the consequences of greenhouse gas emissions and climate change, we expect decisions to be taken speedily, yet the transition needs to be taken place in a manner where you balance the ability to transit, which richer economies can perhaps do faster, with the requirements for development which other economies have. So how does one balance that? So these are the kinds of questions which I hope Dirk will address. Dirk is as I said, the chief scientist at Shell. He obtained a PhD in mathematical physics before teaching at the University of California at Berkeley. He joined Shell in 1992, and he was the chief geophysicist for Shell UK and technology manager for global exploration. And he's currently vice president of exploration technology also. Dirk holds a visiting faculty position at the Earth Sciences Department of the Massachusetts Institute of Technology. He's also has a visiting position at the Indian Institute of Science right here in Bangalore and at other places. He was awarded the Ludwig Mintrop Award in Geophysics from the European Association of Geophysicists, and he's a member of the National Research Council on Solid Earth Observations of the United States and the National Foundation for Fundamental Research on Matter at the Netherlands Organization of Scientific Research. Dirk says that he values science and technology to address major societal challenges and improving people's lives. He's also passionate about science education, and he feels that this is one of the major and unique human capabilities that enables people to change their world and improve the quality of their lives. And this is true in any society, he says, throughout history. And this is very true in India because education is empowering, and today's world, the converse is also true. The absence of education means that it can be very disempowering. So education is a very critical aspect. So as we go forward on an energy transition, the entire population of the world is confronted with this challenge. It's not just a national problem or a local problem. It affects everyone. And therefore, the complexity and nuances of addressing these are a very big challenge. And here it requires all of us to listen to each other, to different viewpoints, to different kinds of solutions, and see how we can go forward both in the short term, but also in the midterm in this very urgent situation. So with that, I warmly welcome Dirk here and look forward to hearing him. Dirk, thank you.
Now I need to switch this on. Do you hear me?
Yeah.
Good. Well, thank you very much, Vijay, for this. Think about an energy transition that affects all of us, or at least is meant to affect all of us, rather than a few happy people who can afford it, say, or for that matter, the people who suffer from some of the consequences if not done right or not done in a way that would serve the world population. This is something that is very core and dear to the company that I work for, who really believes that energy should be accessible to all. And in fact, going forward, clean energy should be accessible to all, which means it needs to be affordable to all. And that means that there are trade-offs and important dilemmas that you will find on the way to get there that are more complicated than perhaps a single-minded view would be for perhaps a large group of people, but still only a subset of the world population. we really believe in inclusiveness in these discussions. Inevitably, you will therefore also enter debate. Before I enter that debate, I need to give you a cautionary note that in essence tells you that I am, as Vijay said, the chief scientist for Shell. My views are in that sense not necessarily reflecting what Shell's current business strategy is. This has nothing to do with the fact that Shell doesn't believe what I'm saying, but it simply takes time to implement things that people do or think about and discuss within the company. As a result of that, you shouldn't buy or sell your shares in Shell as a result of what I mention here. Well, what I'd really like to take you through is, first of all, that energy transitions are perhaps rare, and they're unique moments in human history at which there is a distinct opportunity to improve people's lives, or our lives. And what is known about energy transitions is that power densities, which I will define in a minute, really matter. Oftentimes, people don't realize power densities as rule in energy transitions. That's something that I find as a physicist very remarkable, because that's one of the first things you would ask when you convert energy or when you indeed transform energy into other things. What is the power density that allows you to make that, let alone at scale? Then I will actually show you that indeed there is a real need for action to accelerate relative to the current pace of an energy transition to net zero emissions. That is not a small statement. You could argue that it is driven by the fact that Paris, or the Paris Agreement, stipulate that in 30 years from now, we need to be staying within 1.5 degrees of global warming. In essence, that has nothing to do with how perhaps the energy transition may take shape. These are two different timescales perhaps involved. Whether they are compatible is something that is not necessarily always the case for some of the solutions that people put forward. And that is where the complexity actually starts. I will show that some of the drivers actually require significant energy storage and transport by looking back at the previous energy transition and understanding why did that scale so fast. And I will actually also say something about capacity factors, that is the ability to generate energy and indeed also power on a sustained basis, a predictable basis, using the infrastructure optimally. And that sets me up then to conclude, how do you achieve large scale, which is conceptually not so different or not so difficult to understand, but sometimes remarkably also overlooked in my view. And then if I have time, I will give you a conclusion that you may take home and reflect on. Let me start with probably some of the more difficult concepts that I will discuss this evening, and that is the concept of power densities. If you look at the left, then what you see here is a transition over time. On the horizontal axis is time, and on the vertical axis is the percentage, say, of a certain energy type used in society. So never mind that the energy total use grew, of course, for Germany going from 1815 into the 2000s, but I'm interested in the relative composition of the types of energy sources used. And what you can see here is that around 1815, most people were living in rural communities, in sustenance farming, and did manual labor work to actually cater for their lives. And that transitioned roughly coinciding with the industrial revolution that took a little earlier place in the UK, or in England for that matter, where coal actually started to become important. What is significant, if you go from left to right and see from, say, at 60% levels that you indeed take from human labor to coal and eventually to oil, and perhaps even to gas, is that each time the energy or the power density at which people used conversions of energy for useful work increased. That's a very significant statement to make. These power densities actually rule how you use energy in usable work. Exergy, people are referring to that as well. And that is something that is explained very well by Václav Smil, a friend of mine, who actually wrote already decades ago about the concepts of power densities. What you see here is watt per square meter, power per square meter, not really a density, it's an areal density, versus the area that it takes to build infrastructure to generate that power per square meter. What you see, and it's a logarithmic scale on both axes. And what you see here are in blue uses of or production of energies, so energy sources, wind, photosynthesis, oil, coal fields. And in red you see the uses of energy. The consumers, if you wish, cities, houses, supermarkets, high-rises, industries, steel mills, etc. And what I plotted in here, following Václav Smil's idea, is what are sort of roughly the power densities used in these consumer units, but also relative to what the sources are where you obtain these energies from. And what you see immediately is that what we currently live in an oil and gas age is that the power densities of the sources are roughly similar to the power densities of our consumption. It's not necessarily true that the two need to be absolutely identical, but as I will show you, it helps a lot. And if it isn't, as for a case of wind and photosynthesis, photovoltaics is much better, tidal or hydro for that matter, renewable sources in other words, the power densities in generally are much less. Well, let's see how power densities work in practice. This is a map of Manhattan. And what you see here in red are high power density users per block in Manhattan. In fact, I would advise you to go to this website because the map is actually dynamic. You can look at it per hour, at least at the times that I looked it up. Maybe they took it off now. But you can indeed see how the coloring, i.e. the amount of power per square meter used on Manhattan and also in Queens and in Brooklyn, by the way, how that varies over the day. Not surprising, around 8 o'clock, the power density shoots up because many people literally working on top of each other use a lot of power, at least their computers, but also probably other things. There's a lot of industry in Manhattan too. Many people don't know this, but there's a lot of small industries as well. And hence you see that there is a lot of power used because the power actually that is used in terms of energy is kilowatt hours, is 2,000 kilowatt hours per square meter on an annual scale. That's a lot. It equates to about 100 watts per square meter continuously. A solar farm is about 5. So in other words, if you would like to see power generated for Manhattan to be driven by solar panels put on roofs, then I can tell you the area in New York, of the city of New York, is not enough to generate all that power and densify it into users of Manhattan. New York will have to have its energy coming from elsewhere, at least to a large degree. Now, keep that in the back of your mind. Power densities are important, and you will see in a moment why. What you see when you look back at a world energy system, then roughly starting at the Industrial Revolution, the uses of energy really took off. In a matter of just a few decades, the energy system multiplied many, many times. That is remarkable. In fact, the actual takeover of oil and gas happened in maybe 50, 60 years. That is unusually fast. In fact, the way that was happened is one of the things I will explain. And companies like Shell, that started off very, very small, not in the 1920s, actually had a large role in that, in facilitating or in building infrastructure and also building the capabilities to scale up fast. I will come back to that in a minute. What is important though is that as now, as was also true in the Industrial Revolution and was also true in other energy transitions before that, there are 3 drivers or 3 challenges that continuously force you to make trade-offs. Those drivers or challenges, if you wish, will only appear at a very large scale. They won't really come up or surface so much, say, at a small scale. It's the economy, the environment, and security. Security of supply is something that is very big now in Europe 40% of our oil and gas supplies in Europe are essentially coming out of Russia. And we found out that Russia had different values than perhaps the West had. And now, essentially, we are suffering from supplies that are made now political instruments that actually create a significant increase in gas prices on top of perhaps what was already happening, as well as uncertainty of whether there will be enough energy in Europe for the coming winter. So if you are indeed designing a new system, if you wish, or would like to transition, at some point you will need to realize, well, what are really the dependencies that are implied by that? You may become dependent, materials or resources, raw materials, or otherwise dependent on capabilities that you fundamentally do not want to be an entire country to become dependent on. And usually when people start to realize that, it's too late, like we do in Europe. The US in that sense was far better. In 1974, when the oil crisis hit, most of you may not have been born then, but I was, and we had in the Netherlands weekends that there was no driving possible to save energy. It was unheard of in a rich country to all of a sudden be forced to be sitting at home. The US at that time realized we won't want to become dependent on oil out of Arabia. It took 40 years for the US to actually become completely self-independent of energy resource. Of course, in these 40 years, the energy consumption in the US grew as well. So it's not a static thing. In Europe, that didn't happen. There were reasons for that. It's not because Europeans were particularly stupid, but there were reasons for that. I'm not going to go explain that. But now we pay a price that we are, in fact, much more dependent than we thought. The same is true for the environment. Maybe back in the Industrial Revolution, the environment was more locally. Now we face an environmental threat that is systemic. It's systemic in the sense that it affects all of us, whether you're part of this transition or the previous transition or not. And lastly, economics. The scale up in an energy system that is needed to become affordable for everyone or accessible to everyone is such that you cannot expect governments to continuously support or finance the energy supply. That is impossible. You can make incentives to set people into the right direction and to build, say, facilities and to stimulate developments, but at some point an economic model needs to be behind it. People need to make money, and in fact, lots of people need to make money. There's a self-sustaining driver that money that is made, or income that is made, value that is created, so to say, needs to be plowed back into, say, the development of infrastructure. So economics is very important to get access or to build the required infrastructures that are inevitably needed to become scale. Now, there are economic models already quite old that actually show how such a transition happens. That, for example, as I showed in Germany, started with people who were basically all living in sustenance farming, essentially also in quite poor conditions. At some point, driven by the opportunity provided by technology, as well as the fact that there was an emerging middle class that was already present in the UK, not very big, but large enough, it was possible that these technologies started to build an economic model and a way of manufacturing that multiplied faster than the size of the population actually grew. By which I mean access to the technology is of course quite fast if everyone wants it. You need to outpace this. So there has to be an exponential growth in the ability to essentially transition to, say, users of coal in this case, and later on in oil and gas. So in other words, there is far more technical opportunities that people claim would improve our lives, may fail simply because they don't spread enough, they cannot scale fast enough. The benefits are immediately distributed over an ever larger group of people, and essentially everyone will then end up all a little richer, but there is no net wealth created. This is something that I would say, is in the area that people can make things. This is when you start to see big manufacturing industries occur and grow fast. This is made possible by power densities accessible, allowing you to make energy conversions, chemical conversions in particular, that were previously not possible or not reachable simply because the temperatures were not reachable and also not very efficient. And then at some point, people, you could argue, are getting richer and richer, and at some point the economic growth decouples from the actual energy consumption. Because during that exponential make phase, the energy uses increase also quite fast. And if you compare this now, say, to the current situation, then indeed you see, as measured by emissions, ironically, that's a very good measure to measure how energy is actually used, in particular where. Compare, for example, India with the United Kingdom. You can take any country in Europe. If you take the US, it's a bit messier, so that's why I didn't do it, and I had to explain a lot more. What I plotted here, or what is plotted here, because these data you can find in Our World in Data, is the GDP and the emissions produced mainly by heavy industries. Not all, but that's a large factor. And there's a strong coupling. The reason is that the growth in GDP in India is very much tied to the production of goods coming out of cement, steel, ammonia, plastics. Those 4 or 5 basic industries explain a disproportional amount of these emissions. In the UK, that's no longer the case. And in fact, you see the decoupling of GDP from these emissions, in fact, from energy. You also see something else, which is interesting to look at. You see here consumption-based CO2 emissions in red and production-based CO2 emissions in blue. The production is what the factory makes. What the consumption is what society does in India, and likewise in the UK. But you see in the UK it's flipped. What happened in the UK is that people outsource these heavy industries. It's hard work, hard labor, dirty, a lot of pollution implied if you don't do it right, and sometimes that happens. So people would like to sort of get other people doing it. It's an opportunity for China, India, Indonesia, in fact countries in Asia that have now large numbers of middle-class people entering the middle class. It's an opportunity to actually build these production facilities and export that for top dollar into these countries. That's why you see that the production-based CO2 emissions in India are higher than what society itself in India would use. In China, it's even more dramatic. There's about 1 billion tons of CO2 on an annual basis difference between the production that China does make, because they export a lot. And that brings me to the following point. The fact that these heavy industries or these high temperature process industries take such a huge amount of emissions as they're responsible for, is outpacing the decline, say, in emissions, relatively speaking, in the West. Hopefully that will change, but that's still not the case. And that makes that the actual and absolute emissions over time today are still increasing, even during COVID. So the growth, say, in countries like India, in particular in Asia and Latin America, is faster, attracting more, manufacturing industries, working faster, that outpaces, say, the efficiencies that allow people to become more energy conservative, as well as make different production processes. And hence what you see, for example, in the United States is that there is a strong peak, but that peak was in the 1950s and 60s, exactly caused by steel, cement, plastics. It's now shifting to China, India, or to other countries in Asia. There's nothing wrong with that. That's how you actually create wealth in a society where an emerging middle class is occurring. But that's the backdrop. And you see what I'm getting at. There are huge differences on how to decarbonize these systems between developing economies and developed economies, if there is such a word. That people need to respect. There's no one-size-fits-all solution. And if you look at, say, a graph that I still don't understand fully what Human Development Index really is. But if it is some measurement that people intuitively relate to, that we could argue says something about the quality of your life, perhaps, maybe that's a different dangerous statement to make, versus the amount of energy that you use, then it's very clear. There are some countries like the US and Canada actually use an extraordinary amount of energy per person. And maybe countries like Japan, Spain, the UK, in Europe, actually are a little bit more moderate, if you wish, but still spend a lot more, have a lot more quality of their lives. You could also argue this is where the large classes of the middle class actually have occurred. In Spain and in Japan, the middle classes are larger than 80 to 90% of the population. But that's not true in India. In India, you can see that already if you just measure what is the amount of energy or electricity that is used. Today, it's about 1.6 thousand or 1,600 terawatt hour on an annual basis. It may sound like a huge number, but it's peanuts compared to the same amount of people would have lived in the US, would have consumed if they would have lived the same way. It will grow to about 25 to 30K. That is when you reach more or less this point over here. And that would mean that the average income in India would probably grow by an order of magnitude. That would become sort of an average income in Japan. Of course, in Japan you have ultra-rich people, you also have poor people, but 90% of the population is in the middle class. Have a decent life, if you wish. Or at least, I haven't asked the Japanese whether they really think they have a decent life, but I would argue by analogy with other countries, in particular my own, people would probably argue that there is a decent life. And that is where I think some of the problems start to hit you. Because that young lady over there is now faced with a fantastic, sobering reality. Because at that scale that the energy system has grown so far, a systemic environmental problem is occurring that affects all of us, not just, say, the countries that have managed to develop a little further. And it's very clear that even the pledges made at COP26, and even the more ambitious pledges, perhaps even, that were not written down, are all not sufficient to keep us within that 1.5 degree, say, at least as far as we can assess today. So what do? It's basically a result of the fact that, yes, maybe in the West things are starting to improve, but it's not by a long shot enough to offset, say, the actual growth that is projected by the 3 billion people that will enter the middle class in Asia and go through something similar as what happened, if you're not careful, with the Industrial Revolution. Or put differently, there's probably only 30 to 40% of the world population that really went through the Industrial Revolution. In other words, 60% of the world population, or probably even more, still lives in conditions that you could argue are characterizable by pre-Industrial Revolution conditions. These people will grow as well. Once they start to become close to the middle class, the opportunity is there, the technologies are there. The technologies of the past are certainly there. So we face a significant issue. And one of the things that I would like you to take home with is not so much what my preferred solutions would be. I don't have preferred solutions. But whenever I teach or talk about energy transitions, I would like to make sure that people understand that the complexity of what needs to happen, if only because there are really different regional differences on how to approach this problem, require a much more nuanced debate than the simple statement that you sometimes hear in the West, well, we need to electrify everything. I'm not against and even believe that Greenpeace at the end of the day probably is right. And that in future, some far future perhaps, or hopefully sooner, everything might be indeed resourced renewably. But that is unlikely to be in time for Paris. And my talk, in essence, shows that there are other ways, more optional ways, more optionality and more flexibility needed, in particular to help growing industries in developing countries to decarbonize in different ways than just demanding that we need to electrify. That doesn't mean that I'm against electrification, not at all. That needs to grow a lot, and Shell is actually doing that also in this country. We make huge investments in solar farms, etc. But that will not be enough, in my view, and I know that I have not everyone on board in Shell with that, to be honest, but it won't be enough, in my view, to actually really make a credible proposition to to policymakers, to society, that there is a path towards 1.5 degrees, unless you are prepared to really think a bit bigger and think more systematic. What is at stake is that we essentially grew very complacent and almost ignorant that oil that we use today, and for gas a similar statement is true, but oil is a much more, can be much more illustrative in that sense, is both a high energy density source, but it is also a very good energy carrier. I may state things that are obvious to you. We put it in big tankers, huge tankers in fact, and that ship out of the Middle East or out of Houston or out of China or other where big basins, oil basins are, to any customer in the world. And now I come to another important statement. That energy carrier is of course very dense. So this tanker represents an enormous energy value. It's huge, billions. And the trading in energy is actually happening on these routes. There's a lot of trade happening as energy is moved through oil from A to B. You may be surprised, but the cargo in a tanker, not every tanker, but the cargo in a tanker changes hands multiple times to allow an energy trading system to work. So people make money just simply because of the fact that it is representative of an enormous amount of energy that potentially could be used for something and needed to be as an underwriting for some other energy project, say. These energy trading mechanisms are hugely critical to make an economic model work to build global supply chains connecting resources to customers. That's how the oil industry actually built scale. It's not done, of course, it was not done in isolation. Governments stimulated that. But the fact that the societies were able to build global supply chains to connect only a handful of basins, I will tell you later how few, to connect any customer in the world, in principle, with affordable oil, at least as far as, say, these companies are concerned, barring any geopolitical statement. If people start to do a war, then it changes. But I would argue that's hardly, say, under the control of a free market. That overcomes, hopefully it won't too much. So, but these supply chains are a vital element to build scale. Now you switch to something that is renewable. And now you see also perhaps the danger of insisting everything needs to become renewable. At the start, it may eventually become renewable. You get into low power density sources. And what is more important perhaps for renewable sources, they're also intermittent. The sun doesn't always shine and the wind doesn't always blow. I will show you what that means. The solution to that is that you actually change now to explicitly different energy carriers to transport the energy that you get out of renewable systems. It's not true. The wind blows everywhere sometime. But there will be places on Earth that are far better for wind or for solar. Anyone can think of a desert. The Thar Desert is probably a better place to put your solar panels in than maybe someplace south in India. And that is similarly true for wind farms. But then what do? Rather than transporting that flow of energy, flow of electrons, building it into now explicitly designed energy carriers by chemistry is maybe not a bad idea. And why do I say that? Well, first of all, renewable energy actually suffers from this intermittency, and everyone has seen those graphs where you get negative energy or electricity prices when there's more energy provided to the grid or electricity provided than there are consumers. That's fatal for any industry that wants to decarbonize. It's fatal for these fluctuations are not tolerable. The reason being that you need to moderate this. There may not be enough. If you run a chemical factory or a manufacturing factory, you would like to have stable supply of energy. That's how your energy or your production processes are organized. What you see here in red is a California energy system that actually, a power grid on average, that was still at the time that most of California's power was powered by natural gas and nuclear. In 2017, there was a lot more installed capacity for solar and wind. But the interesting bit is, this is a slightly difficult plot perhaps, this shows as in fraction of installed capacity for wind and solar together in California and the total output. And these numbers are in megawatt. And California has about 18 gigawatt installed capacity of solar and wind. The numbers don't matter that much. But what is absolutely astonishing is that only 10% of the time, about zero wind is present. So you cannot build enough, I say, to overcome that. If there are days that there are no wind, effectively, it doesn't matter how much solar panels or wind farms you. The other irony is that California, and that is not unique, although it's not everywhere either, on days that there is no wind, usually the sun is so hot or the temperature is so hot that solar doesn't work either. So there is a correlation in the intermittency. That is not true in northern latitudes. It's true in areas in California, in desert areas. I don't know what it is in the Thar Desert, but I would not be surprised that wind and solar intermittency are actually far more coupled than we believe. And a large time zero is still zero. The other thing that is important is that of 50% of the actual installed capacity is only used 22% of the time. What kind of system is that? A gas-powered or coal-fired power plant has a capacity factor of above 60% or 65%. So if you want to cater for intermittency by overbuilding, well, think again. That's a huge amount of steel, glass, concrete, etc. that you need to build only because it's such a lousy system. And you come from a world where those efficiencies finally were managed into a system that had these large capacity factors. So it requires quite a lot of engineering and innovation to actually try to overcome this. Another way of stating that is that, well, if renewables you want to scale, energy storage becomes important. And I'll come back to the statement I made around chemical energy carriers. And my big mentor here, Steve Chu, told me it's good at this point in the talk to sort of give a bit of a quiz to wake you up. So, what does a Boeing 777 have in common with a bar-tailed godwit? And I know godwits are also here in the Sunderbarns. I'm a birder. This picture I make myself in the Netherlands because a godwit is the national bird in the Netherlands. Unfortunately, fewer and fewer godwits choose the Netherlands, so soon we will change the national bird because no one will know what godwit would look like anymore. Any idea what this difference is? What this correspondence is? Well, both can fly non-stop 11,000 kilometers. And at takeoff, 50% of the actual weight that is lifting off is fuel. Or, in my speak, a chemical energy carrier. What does that do? It allows that godwit, not just one, but thousands, to navigate from A to B. No godwit ever travels the same route. They roughly start from, say, areas in China, if the godwits are from India and Bangladesh, and they then land in the Sunderbans. But the Sunderbans is a big area, so they never go to the same place. It's not exactly the same. What is required, what turns out to be the case, it's another talk that I sometimes give for an ornithological society in the Netherlands, is that it's for the first time we actually proved with sensors that these godwits actually fly straight over the Himalayas. So they not only lift off, but they lift off a lot, to 7,000 meters. They don't do this by not carefully thinking, what is the opportunity, how do I make use of energy conservation as best as I can? What helps is if you are really flexible and have a lot of options. Chemical energy carriers allow you to do that. Also in our energy system. The tankers may actually flow from Houston to, let's say, Amsterdam, or sail from Houston to Amsterdam. But if it so happens that the trade is something else, then that Houston tanker may actually go somewhere else. And there's another tanker then coming into Amsterdam. And guess what? No consumer actually feels any of the difference. That system is so large and so flexible and so optional that it doesn't matter. If an oil rig or a platform in the Gulf of Mexico actually is shut down, let's say because of a hurricane, then tens of thousands of barrels a day are missed. There's not a single effect on the oil price. And if it is, it's a glitch. What really makes the oil price change, there are far more geopolitical or other effects that are much more systemic. It's not those things. So what I'm actually now trying to draw your attention to is those chemical energy carriers. While we also start to tell you now what really, say, sources of energy are that you could argue are clean, or no hydrocarbons, or no carbon in it, or carbon that has already been in the atmosphere taken up by plants, say, that's what I mean by bio-waste. That doesn't mean that you can then burn that at free will and then sort of claim, well, look, I mean, it was already in the plant, because the timescales are different. You do need to do something called CCS or something else perhaps to do that, or just use it for different things. But what I try to plot you here is that renewables, nuclear energy, we'll pay a bit of attention to that later, bio-waste and oil and gas, let's say in the next 5 years, will probably play still a very big role, maybe even 10 years. And that is what depicted by those lines. The fatter the arrow, the more energy source is used to either power the grid, make those chemical energy carriers, other things than just oil, or just simply get the oil and fuels, say, from refineries. And then I would like to draw your attention to how we use it. So these are the consumers. That's residential homes, personal mobility, heavy-duty mobility, factories, small farm mom and pop shops of industries, as well as big steel companies or cement. And I distinguish them between the lower power density and the higher power density ones. There's not a really solid line that defines one or the other, but at some point you're far less interested or you're far more vulnerable to intermittency, simply because the organization of a high power density industry is via big plants. A steel plant making just 1 kilogram of steel per year is not profitable. You need a steel plant of, let's say, a few million tons per year. Then scale actually works for that plant to make it profitable. That's true for cement, slightly less. It's certainly true for petrochemicals. A usual petrochemical plant is in the order of 200,000 barrels a day equivalent output. If it makes it smaller, no one will make money. The plant will not be built. That makes it different for lower power densities. The amount of energy may be the same, but you can deal with smaller units for consumption. Your car is not a plant. And it's also more distributed, which helps a lot to overcome low power densities. If you use it over larger areas, the power densities match easier. And you will see here that there is a heavy dependence on oil and gas, presumably, but you also see that renewables first go into a power grid. That makes sense, because if coal is used to generate power, replacing that with renewables saves a lot of emissions. Don't do anything else. Switch off the coal-fired power plants first with renewables. Anyone who tries to convince you of something else, I'm not saying is the wrong thing, but be careful with what you ask for. Because it makes a lot of sense when it comes down to emissions to first switch off coal-fired power plants. And that then essentially means that the grid in the next 10 years will basically go into residential home cooling and heating, maybe your Tesla, if you can afford it, or another electric car. It will not go so much in high power density industries like steel yet. I will show you in a minute a very graphic example of that. But in the future, so somewhat further out, you can start to see that gas may still hang on, but oil may not be so needed anymore, because what we've learned in the biowaste, nuclear and renewables is to generate chemical energy carriers to connect resources with consumers. And we presumably also learned how to actually build factories that are fed by these energy carriers like hydrogen, methanol, ammonia. That is already happening. Out of the Middle East, tankers with ammonia or hydrogen are already shipping to consumers that switch from oil or gas to hydrogen. Either because they diversify their gas business through that, because they go for blue hydrogen perhaps, or hydrogen that is made with renewables. In the Middle East there's a lot of deserts, there's a lot of space. And that brings me to another point. Those transitions will happen everywhere, but generally speaking, you can see a rise in an increase in the use of chemical energy carriers to essentially compensate or to mitigate some of the undesired consequences of switching too much to renewables. It allows, therefore, renewables to grow, because if you don't, you may actually see an impediment or an hampering of scaling renewables simply because those users will not accept that. And indeed, the hydrogen market is projected to grow significantly beyond what it is already. There are three ways of making hydrogen other than through electrolysis. There are many, perhaps, but let's say three that come to mind. One is a very well-known technique using natural gas. It's called partial oxidation. It uses natural gas. In order to make that clean, you need CCS. Otherwise, nothing will change, or at least you get the emissions that are implied by burning or treating methane. Gasification of bio and waste, as well as nuclear heat and power into higher temperature electrolyzers. And this is the new kid on the block that I will spend a bit more time on. But first I'd like to give you a hopefully graphic example that what happens, say, in steel. Steel was actually seriously considering switching from coal, a coal-driven process, to an entirely different manufacturing process that is based on either natural gas or in future completely hydrogen and electrification. I'm not a steel expert, so the words I say here will sound silly, but what I understand is more or less around this lot. You have a direct reduction of ore mechanism that is fed by hydrogen, which is 5 times more dense than coal in energy, and electrification of electric arches that actually do following processes. As a result of that, there's a significant reduction in CO2 emissions possible in the steel industry. It also makes up for a much more compact plant. This is a plant in Sweden, the first one, a demonstration that actually does this. But what you show there in text beneath there is that there is a minimum size, as I said, to these plants. A steel plant in the Netherlands uses about 350 kilotons of hydrogen if it were to be run out of a process that is fed by hydrogen and electricity. That's a lot. How much? Well, here's the table that actually tells you how much ton hydrogen you could get per square kilometer per year, which is of interest to a steel plant because they buy in annual batches, with a long-term view, of course, either by solar or by offshore. That is not a whole lot. If you do this in wind, because the sun is not so shining much in the Netherlands, except for this summer, it was really good, but most of the time that's not the case. Wind is much more available. But 350 kiloton of hydrogen equates to that sort of box, red box here in front of the Dutch coast. Not exactly a sea that no one is using. This is a huge intervention of existing uses of sea. I mean, the port of Amsterdam is right in front of that box. And this is just for one steel plant. Now, we don't have many more steel plants, so that may be good, but there are other high energy consuming industries, ammonia, chemical industries. They would like to be powered by wind as well. So you can easily see that this grows very fast. Why do I mention this? The population density of the Netherlands happens to be this year, I don't know how robust that number really is, but it happens to be true this year, the same as in India. And think about that. That means that those areas of land used for energy, for consumption, is roughly scalable. Yeah, of course, you're 80 times more bigger. India is 80 times larger than the Netherlands, a tiny country. But there are not 1.5 billion people living in the Netherlands. Only 16, among quotes, million. Roughly sort of the amount that you would get if you would fill up a country 80 times larger. Now you start to see what it means for a size of the Netherlands and on a European scale of how much wind and solar you would have. If you would displace all the diesel today in India, consumed in India, by hydrogen, which is not outlandish because hydrogen starts to become competitive with diesel in the US in some areas. Let's assume that for a factor that is competitively possible, or competitively makes sense. Then all of the Western continental shelf is either wind farm for that diesel to be generated via or replaced by hydrogen made out of green or renewables, or 15% of the Thar Desert in solar farms. That may be satisfying for now, but as I said, the use of diesel will grow up. What I could find from several sources is that it is about, in the next 10 years, 1.5 to 2 times. It may actually grow much faster, depending on who you believe. I also understand that there may be other views that diesel may not grow, but the amount of energy displaced by hydrogen that will then be used might actually explain the growth. And then quickly you will see you'll run out of essentially territorial waters to put all your wind farms in. So this shows that there is a scaling problem here that is similar to what happens in the Netherlands. And I can assure you, we are also having a free democracy in the Netherlands. The amount of permitting that it takes to build this amount of wind farms is simply, well, long, let's put it that way. Because it's not true that the land is barren and is not used, or the sea is not used. And I predict, I'm not very good at predictions, but I predict that that is not so different here. People will balk at interventions to build every, say, square kilometer of sea surface for wind farms. Now, I'm not saying that that is impossible. For sure it won't. What I'm actually telling you is that perhaps by insisting on renewable solutions only without actually showing some of these consequences, and I may make a few round-off errors here, I invite you to do the calculations yourself, but you get the picture. You need a lot of surface area to do this. Actually will drive other conversations. It also actually is a matter of cost. The capacity factor of a wind farm is lower than, say, of gas, or for that matter, of nuclear. In fact, with Eric Ingersoll, we computed what that, or he computed the sort of minimum cost that you could expect to happen. Because as I said, the capacity factor is not always something that you will be able to offset entirely. It's certainly not, say, in cases where there is intermittency going into zero. He argues that it is probably hovering around $4 or $3 per kilogram of hydrogen. That is not low enough for a steel industry to really work on. It needs to be below $1. So you need to do something else. It will take time to figure out how to do that with renewable resources. I'm not saying that that is impossible. There's no fundamental law that tells you that this cannot happen with renewables. The question is how fast it can happen at scale. It's not enough to have 100 kilograms of hydrogen to be produced from renewables at a dollar per kilogram. And that goes away with the fact that we can actually bulk carriers make, like hydrogen, in bulk and ship that, say, to any customer in the world. And I would argue building up supply chains faster as an alternative to allow industries like steel, cement to use hydrogen and other carriers to really decarbonize their processes actually takes away the bottleneck, perhaps, in ramping up renewables fast enough to get all those carriers out of renewables. So you will need to sort of make a balance there, an educated guess, where would you put your bets. As soon as the steel industry moved to hydrogen, it is irrelevant whether that hydrogen came from renewables or whether it has come first, say, from nuclear or otherwise. Of course, there are investments implied by renewables and by, I think, that last over decades, but at least you can make a start to make switches to systems changes. Those heavy industries have another property that I didn't have no time to mention that here, namely that a lot of the emissions are caused by the making process itself, not by the fuel you use. It's true that the fuel also produces, say, emissions, but more than 50% in all these high temperature process industries is actually sitting in the process itself. That needs to change. A CEO of a steel plant is not going to change anything if he doesn't get enough low-cost hydrogen. Why would he? He will go bankrupt. There's no government that can bail him out for that. So the delay to wait for renewables to come at low-cost hydrogen, and for that matter other chemical things, actually drives a delay in the decarbonization that in effect is more productive at the systems change than in the fuel itself. But you will need both. So in other words, my statement is that in order to actually make these processes change to adopt energy carriers that are made by the type of energies that I showed, you probably allow renewables to scale up faster in those areas where they can go and have no competition, say, from heavy industries. And then eventually they will merge. And hence, let me finish off with a few words on nuclear. Oh, it's not true that when I use the word nuclear, advanced nuclear is what I'm looking at. These are small modular reactors, and these small modular reactors are so small that they can be made in factories, and essentially have manufacturing costs or building costs that are much lower. They're also using different fuels, not all of them, but the trend is to use different fuels. If they are dispatchable out of a factory, you can bring the nuclear source to the site, to the industrial site, rather than getting the electricity from a faraway site of a massive nuclear power plant that gets you electricity either to the grid or to a company. And there are a few cartoons. Wrote a paper together with people at MIT on nuclear batteries. These are 35 megawatt batteries. You can actually make, say, complete truck stops using off-grid nuclear batteries to provide hydrogen for large amounts of trucks. Completely off-grid solution. So they give you an enormous amount of flexibility in decarbonization of industries as well as heavy-duty mobility. And finally, a refinery or how to make some of these chemical energy carriers may actually change simply to use the carbon that you use. You saw that I used methanol, for example, and then maybe other hydrocarbon fuels, of which you can take the carbon from, say, bio or agricultural waste. Don't use it to fuel this system. Use it just for the source of carbon. And Charles Vosberg of MIT actually showed that you could double the output of these plants and actually scale it up to about the size of a refinery that we are having today. And I may wonder, what is Shell really doing? Well, we have 5 programs in our research and technical divisions that actually look at enabling all these enablers or all these factors that I just mentioned, in particular around hydrogen, electrification, let's say, of lower power densities perhaps first, but also, of course, with a keen eye on high power density industries. Looking at CCS, we know how to put stuff in the ground. Circular and bio products that are, say, talking to, say, new refinery systems. And what I haven't been able to talk to you about is how do we actually use agricultural advances to increase fertility or increase food production by actually storing more carbon in carbon-poor soils that are used in agriculture. That's a different talk in itself. So now I would like to conclude. You could ask, where would you build those chemical plants? Well, my view is you don't have to build them really. You can start in some of the oil basins or gas basins that are unique in their shift or ability to shift to renewables fast. It's something that people actually don't realize. Of course, there will be new basins needed as well, but you will now realize that it helps to get the best resources in wind, the best resources in solar, the best resources perhaps in bio to factor in there. That is not uniformly distributed in the world, like oil and gas is not uniformly distributed in the world. You may actually have, you can do a study, Wood Mackenzie actually just published something that, which we did our calculations ourselves. There's only a few basins that produce a lot of the oil that we use today. And about 50% or 30% of those are actually very relevant in making shifts towards renewables. For example, because at the same time they give fantastic opportunities for large-scale CCS. Or there are large chemical carrier companies already present because of the fact that these are super basins to produce oil and gas. So it already led to an infrastructure that will then become faster available for large-scale distribution to customers around the world than perhaps a completely new basin would do. But no doubt, these new basins that I plotted here might actually come on stream as well. In that sense, it's very similar to what oil actually started to grow. This supply chain to allow systems of industries co-located because it makes sense either to share resource or to share infrastructure or to allow an economic model to grow faster and thereby making money earlier, is actually not a bad idea to use also in the scaling up of renewable or decarbonized energy sources. And you can even think of offshore engineering systems that are far more compact. Engineering is not the same as it was, say, 50, 60 years ago. And these are actually techniques that the offshore industry, not just, say, oil companies, but any offshore industry, is actually looking at FPSOs for combined production of ammonia, hydrogen, powered perhaps by a small modular reactor offshore, moored in a wind farm. We have no cable connections or very short cable connections. CCS in India is something that I wished I could talk about. I think it's largely underestimated. It's true that there's about 5 to 6 gigaton of CO2 to be sequestered given the amount of oil and gas fields in India. But there is a vast amount of saline aquifers that you could use to store CO2 in as well. And there, India in particular, in the north, is highly enriched. And these are something that I would suggest you really use if you would like to start, say, new energy basins. CCS might be relevant to offset or to at least allow a coal to gas or a coal to renewable transition to happen that and decouple that from the climate problem. So in conclusion, there's a huge difference depending on economic development of where really the priorities would sit. But both are end members of a system that is driven by power densities and by capacity factors. We never talked about capacity factors when the capacity factors are high enough. But when they start to become low, it matters to really understand what you need to do, and you then need to decouple, say, the resource from perhaps the carrier that you need for transport and storage. And in order to do that, it makes sense then to look at what is then the main energy uses that you would like to decarbonize first. And in countries in India, that might be different, given the enormous growth that needs to happen, versus, say, developed countries, where that growth will be different, simply because those industries, for example, are far less present. And that's where I would stop. So thanks a lot for your time.